Hi there, this is the pre-class video for class 34. Thanks for watching. Let's go through some of the reading. So we're in chapter 11, section 11.6, superposition principle and skills for analyzing wave processes. So definitely read through this, but the basic idea is you're asking the question, what happens when one wave pulse meets another wave pulse? And they show you that if there's one up pulse and one down pulse and they end up at the same place, they briefly disappear and then reappear again. And if you have two upward pulses going towards each other, then when they meet at the same place, the upright pulses add and then they pass through each other. So there's something called the principle of superposition. It's introduced a little bit more carefully a little farther down. When multiple waves pass through the same medium at the same time, the net displacement at a particular time and location in the medium is the sum of the displacements that would be caused by each wave if it were alone in the medium at that time. So y net equals y1 plus y2 plus however many waves are being combined at that position. So that's for wave pulses. We're next going to analyze, I think, some sinusoidal waves. You have these beach balls bouncing, ball A and ball B at two locations, and then over at point C, you're looking at it's at a distance B from B and A from A. These are two different distances, and you want to look at what is the y net, what's the displacement over there. So we're going back actually to chapter 11.2, or sorry, section 11.2, when she introduced the equation for a wave, y equals a times cosine of 2 pi over capital T, lowercase t, minus x over v, x being the position. So we can imagine two different x-axes, one coming from ball B towards the C and one coming from ball A. So these aren't the same direction, xa and xb, but they do mark a distance which can be plugged into this equation. So you end up with ya equals this equation and yb equals this equation. They're almost exactly the same except the distances are different. So if, or they could be the same. If they're both equal, then what you would say is that these waves would arrive in phase. So if one wave causes the point at C to move up, the other one will also cause it to move up. Or down. If one's down, the other one's down. So the idea is that with superposition, if point C is at the same distance from both sources, then the amplitude will be twice the amplitude caused by one wave source at that location. And in fact, it's also true if you skip an entire wavelength. So if A minus B equals n times lambda, n being an integer, then at any of these points, the resultant vibration amplitude is the sum of the amplitude of the individual waves. Then it says, choose a point D that's located at different distances such that, so here's a longer distance B and a shorter distance A. So wave B has traveled a cycle more than wave A. So now they're out of phase. So the wave that goes down at point D from ball B, there's another wave that goes up at that point D from ball A. And those cancel each other out. So, and that's going to be true not just for a half wavelength, but for n plus a half times the wavelength, where n is an integer. So it could be a half if n is 0, could be 1.5 wavelengths. Anytime the difference, A minus B, from these two sources is n plus a half times that wavelength, then there'll be little vibration because the waves will nearly cancel each other. And there's there's an example of how to do some problem solving using this method of superposition. There's that superposition principle. And then they talk about Huygens principle, which is the idea here is that when we have a source and the wave travels outwards, and there's a crest of the wave, for example, out here at some distance, r or something, this line AB, what you can model the wave as is each point on the original wave produces a little wavelet. It's like every point on this crest becomes its own source and then kind of radiates out a little circular wave. But when you add all those little circular waves, you get this new wavefront C to D. The wavelets add to produce a new wavefront CD. So the wave fronts are like the crests of these waves, and they travel outward. And to test it, it's a little hard to see, this is a bit blurry, but if you have a linear wave, so a source that's made of a bunch of oscillators right beside each other, then those wavelets will add to make lines that will go along. But then if you cut out a whole bunch of them and only leave one, then on the other, like have a wall with a little opening in it, it turns out that beyond the opening, since there's only one little wavelet here, it ends up like a point source. So the waves go out as circles, concentric circles beyond the hole in the wall there. Section 11.7 is on sound, and we've already kind of gone through some of this in terms of the intensity parts. But basically, we hear sound when compressions and decompressions of air at the eardrum cause it to vibrate. Human ear is sensitive to a range of frequencies from 20 hertz to 20,000 hertz. Compression waves, or these are longitudinal waves also, in this frequency range are called sound. If you have higher frequencies than 20,000 hertz, that's called ultrasound. Lower frequencies than 20 hertz, that's called infrasound. And many animals can sense ultrasonic or even infrasonic frequencies. There's a sketch of the human ear, good to look at that. This is a compression wave, also called a pressure wave. So the pressure is defined as force divided by area, and that's newtons per meter squared. The air surrounding us in normal conditions has about 10 to the power 5 newtons per square meter of surface. That's called an atmospheric pressure. Don't confuse pressure with power. They both use the letter capital P. And then, so once you've got that pressure, there can be changes in the pressure due to a longitudinal wave, like a sound wave, that make it go up or down. So most people, when they make a plot of a sound wave, they plot delta P versus time. That's really what the sound is. Delta P meaning a slight, like 10 to the minus 5 newtons per meter squared above or below the ambient air pressure, which was 10 to the plus 5 newtons per meter squared. So what you've got here is a positive pressure on your eardrum, and it varies a tiny little bit above and below atmospheric pressure versus time, and that's what sound is. We already talked a little bit about the intensity of sound waves, so I'm going to kind of skip over some of that. Intensity level, decibels, we did that yesterday. What I want to talk about is pitch, frequency, and complex sounds. So pitch is related to frequency, just as the intensity or the amount of energy carried by sound was related to amplitude of the wave. The pitch we hear is related to the frequency. Higher pitch means a sound of a higher frequency. For example, but there's more to sensation than just loudness and pitch. For example, there's another thing called waveforms. An actual wave might have a frequency, but it has different shape, not always a sine curve. And that's why an oboe and a violin might both be playing 440 hertz, but it could sound very different due to the shape of the waveform. So a tuning fork sort of produces a nice sinusoidal wave. Here's a higher frequency, different higher pitch. If you combine two tuning forks, you get that principle of superposition, and you get this different waveform. And that's really, so what's interesting here is that you can make a spectrum now, since we've added these two sine waves, one with a certain frequency, one with another frequency, and they have certain amplitudes. It looks like this higher frequency sine curve is twice the amplitude of the lower frequency sine curve. And this is the waveform. What you can also plot is a spectrum, where now you have frequency on this horizontal axis and the amplitude of each sine wave on the vertical axis. And now you've got that wave 1 represented by this spike, and this wave 2 represented by this spike. So most sounds we hear are complex waves consisting of sinusoidal waves of many different frequencies and amplitudes. And in fact, white noise, which sort of sounds like this, is a mix of all the different frequencies of sine waves. And when you hear that all together, it sort of sounds like that hissing noise. And it's similar, I guess, to light. When you add up a bunch of different frequencies of light, that's when we see white light. So that's why it's called white noise. Here is the waveform of a piano note, for example. And if you look at its frequency, you'll see that it's composed of a whole bunch of different little spikes, so different sine waves. Violin will have a different spectrum. So these spectra are characteristic of the particular musical instruments. So beating, last thing here in this thing is beat and beat frequency, beats. So what this means is that if you have two sound sources that are sinusoidal and they're very close in frequency, then like here, when you add them up, you'll get what are called beats. So here's source 1 and source 2. One is at 10 hertz and one is at 12 hertz. Source 1 is at 10 hertz, 12 hertz. When you add these up, it looks like about every half a second here, what happens is that the sound gets loud. And then in between those loud beats, you get silence. And so that's called beats. There's an equation for beat frequency, which is the beat frequency is the difference, the absolute value of the difference of the frequencies. So for example, back here, you had a 12 hertz and a 10 hertz. 12 minus 10 is 2, so this is a 2 hertz beating. 2 hertz meaning that every half a second you get a beat. So that is how beats work. So that gets you through the reading, which is covered in the questions 1 and 2 of the pre-class quiz due on Monday. Question 3 is based on what's called Class 34 pre-class homework. So you don't turn this in. Basically, it's just to prepare you for that one pre-class quiz question. But I would encourage you to click on it, take a look. It's all based on this PHET simulation, which you click on to open up. It's written and maintained by some people from University of Colorado Boulder. You click the play button and it runs this simulation on your device. So, and you can basically click and move things around. Like if I move that wrench, it sends a wave out. And what you're supposed to do is follow these instructions. So it says first you can adjust the damping. I mean, you can play around with it if you want. You can oscillate the wrench. You can send a pulse, I think, by just clicking that. See what happens. Thing 1 is set the damping to none. Then select pulse, which I've actually already done. And it should be on fixed end. So there are actually different kinds of ends. There's fixed end, which is a clamp. There's loose end, and then there's no end, which is just an open window. So that's always fun. So if you put fixed end and you send, you click on the little green triangle pulse, it should shake the left end of the string. What happens? So I'll let you explore that, kind of try to answer the question. You don't have to turn it in like I say, but just look at it. And then it says select loose end, and again send a pulse and see what happens. I'll just sort of put it there. You can also put it into slow motion. That's another nice thing, so you can actually see things happening a little bit easier. Then the pulse goes along. What do you think is going to happen when it hits the loose end? Give it a try. And then click no end. Same sort of thing. You can always press restart, click the pulse, and this does an actual simulation. If this is a wave on a string, what would happen? Okay. So then there's oscillate. So we're going to try that and press play. And what that does is it sends this sinusoidal wave going along. Does the shape of the sine wave pattern change with time? So that's something to think about. Which way does the pattern move? And look at which way the individual green and red beads move. So you can just sort of stare at this for a little while. This is what's called a traveling sinusoidal wave. Okay. So then step 5 is no end. So that we can set the amplitude here. This is right now 0.75 centimeters. We can set it to 0.1 centimeters. And it wants frequency of 0.42 hertz. Okay. Can't get it there. You can use these little arrows. What this should do is set up a very low amplitude sine wave going out the window. So, and we can put it maybe back into normal speed. So nothing much interesting, but you're supposed to click on fixed end and then sort of see what happens. And this is all about forming standing waves, which is a part of the principle of superposition that we'll be talking about in class. So, and then they ask you to change the frequency. So after you've got fixed end and you have to wait a little while, you gotta be a little patient, try different frequencies. And what they're asking you to do is to find, so if you choose like 84, yeah, 0.84 hertz, that's going to be a different standing wave mode. Press restart, and you should see this situation where you get nodes. So a node is this bead in the middle that isn't shaking very much. Okay. And what they're asking you to do in step 7, and that's the one for the pre-class quiz, is to find a frequency for which all the green beads are nodes. So this has got one node. You want to find a frequency for which all 1, 2, 3, 4, 5, these 5 green beads are nodes. The outer green beads are always nodes, I think, because they don't shake that much. But you want to get these inner 5 to be nodes as well. So I would crank up the frequency to some number, try to find what that frequency is. It's not quite working. It takes a bit of trial and error. That's wrong, because this is definitely not a node. So just keep on searching around. You might be able to kind of figure it out. We know that 0.42 sort of gives no nodes at 0.42 hertz. 0.84 hertz, double that frequency, gives one node in the middle. If you triple the frequency, you might get 3 nodes, etc. You want to try to find one where the frequency here where you're going to get 5 nodes. So maybe play around with it, maybe do some calculations, give it a try, and that will complete your pre-class quiz. And I'll see you in class. Bye for now.